So what about my thermal efficiency? Thermal is equal to work out over U in. And that's going to equal to Cp delta T3 2 minus Cp of T4 minus T1 divided by Cp of T3 minus T2. Again, I'm taking the kinetic energy out because I assumed it's very low velocity. So from that, I'm looking at it from the cycle perspective. But from that, I could simplify these equations, cancel out my CPs, cancel out a few terms, and what do I end up getting? The thermal efficiency is equal to 1 minus T1 over T2. Let's see. So the thermal efficiency is highly driven by my ambient condition temperature relative to my exit temperature. If I bring my exit temperature to a almost equal value to 1, then my thermal efficiency is very low. So from there, let's do the real cycle for the turbojet and write our equations of how do we solve turbojets. Which is the same exact principle. Let me start at a new page. We've done so far. Modeling real turbojets. With or without afterburner.
He doesn't want to write no more.
So here's my TS diagram. And we already know how to treat a real situation, right? We said if I'm starting an ambient condition and I'm going through, so say step through the engine. So the first step is outside the engine. If I have a turbojet that is real, it's not ideal, without an AB. Without an AB is easier because it's sort of a straight curve through the CD nozzle, turbine through the CD nozzle. But with AB, we have that additional expansion. So we'll draw the with AB. So the real turbojet will have pressure losses relative to my ideal turbojet. So my situation is going to be, this is my ideal or isentropic situation, where I'm going to get to a stagnation pressure of POA, right? And I have this an alternative behavior that happens. I'm going to do it with another color. PO2, which is primarily my isentropic S situation, ideal situation for PO2, but the real engine is going to be at that same temperature level as POA, but along this curve. So right there. Plus here. So that's my PO2 actual. So this is the isentropic situation I raised up to here, but no, I actually end up there. So my curve ends up being this for the inlet. Now the same thing I could do for the compressor. Compressor, if it's an ideal compressor, adiabatic and isentropic, it's going to go all the way up right here. And that's point PO3. my real situation is going to be along the same curve of PO3, just something like this. This and we extend it all the way right here. So that's this curve. Right there. So it's almost the same as the inlet. Well, it makes sense because I'm actually applying compression process, but just a larger delta P relative to the inlet diffuser situation. Now, ideally, through my combustor, so this is PO3 actually. So ideally, through my combustor, I have constant pressure combustion, meaning I'm going to use this ignition pressure and ride it all across. But that's not what happens. I have pressure losses through my combustor due to flame holder drag and things like that you've done for problem 2 in the midterm 1. So most likely I'm at a different pressure level. That pressure level is going to be somewhere out there. It's going to be less than PO3, so I'm going to name it PO4. We already did this for ramjets. And through the combustor, so I have nominally constant pressure combustion, but something like this. I think I messed myself up there. Actually, let me do it here, sorry. Let me do PO4 here. It's a complex. PO4. Now, I'm going to have to go through my turbine as well. So I have to go isotropic expansion, get the pressure associated with it. So this pressure is going to be PO5S. So it's 5S. But then my real situation with efficiency losses through my turbine is going to give me PO5, the real stagnation pressure. Now, this is for up to here. Right, so I went through my compressor, I went through my inlet from A, through to the compressor, then through the compressor, so this is my inlet, it's 2, then through my compressor, then through my burner, then through my turbine. Now I need to turn my afterburner on. What do I need to do? It's the same exact principle, right? Like I did for the second burner, the first burner, main burner. I'm not going to be at the same pressure level. The ideal situation is to go like this and then to come down. But for the real situation, I'm not at the same pressure level. I'm going to be at a lower pressure than this one. So I'm going to name this PO6, which is a pressure loss, and this is what I'm going to be adding as heat through my afterburner, and then I come isotropic expansion versus real expansion, same exact principle through my CG nozzle, and then I'm back into this curve right here. So this is 7 versus I'm sorry, this is ambient versus 7 AB, and we could make without the afterburner right here. This is again ambient, and this is 7. So I have two situations where I have the afterburner right here, and the curve comes this way for the real turbojet. But if I turn the AB on, then I'm adding heat at a different pressure level. It's constant pressure burning, but at the same time I have pressure losses, so my ignition pressure is slightly lower. And from there, I have another curve that comes this way. Make sense? So let's outline the procedure of how to solve this in general in the real situation. Outside the engine, I need to go through my compression that's driven by my diffuser. So I need to know my ambient condition. So I know TOA over TA is equal to a function of my Mach number or my flight Mach number and gamma, and from that I can get my TOA. My POA over the static pressure is equal to a function of my Mach number again at gamma, and from that I can get my stagnation pressure at A. From those two, and knowing my static temperature condition, I can get my velocity. My velocity is equal to ma gamma RTA. Stuff that you already know, and we just keep repeating throughout. So now I know my conditions at the ambient that is ramming into my engine, whether it's a turbojet or a ramjet. This is universal. Then I go inlet, diffuser. I have the stagnation temperature at 2 is equal to the stagnation temperature at the ambient condition. Now, why are they equal? Because even if I do have shocks, what is the stagnation pressure? Stagnation temperature across the shock?
Constant.
Constant. So TO and TO2. I get my TO2 there. Now, if I'm trying to dictate my efficiency loss right here, well, it's eta of the diffuser is equal to, and we've done this before, which over which? T. What am I supposed to put here? You should be able to tell from this drawing right there. We've done this.
He's getting mad. He's getting really mad.
What?
He's getting mad.
Okay, so what is my lowest temperature? Is A, right? So everybody agrees that this is A and this is A, right? Okay. What about, what temperature should I put here? If I do O2S here versus O2 here, which one is larger?
No.
O2. So if I did O2 here and I did O2S here, what's going to happen? Okay, very good. So this is O2S. And this
Oh
is
yeah,
O2.
isentropy goes in the top.
And the same thing on the other side, by the way. So I'm going over this so you make sense of it as you're going through. If your efficiency is more than 1, no, it doesn't make any sense. So from there, if I have this, and I have my ambient conditions, so what am I going to get from this is the isentropic temperature. Now that I have my isentropic temperature, I can use that through my isentropic relations to figure out my pressure ratio. So PO2 over POA is equal to TO2S over actual, which is gamma over gamma minus 1. And from that, I get my PO2. So now I know my compression ratio across the diffuser, which is a critical parameter that we need. So let's do the same thing for the compressor. Compressor. It becomes very tedious. It becomes the same all the time. The efficiency of the compressor is the same thing. TO3S, isentropic relative to actual, because isentropic is going to be lower. I can compress it at lower temperature ratio, but I have losses, so I end up generating heat. Sorry, 3. Relative to, sorry, this is to O2. So from that, I can get my TOS3, and from that I can use my isentropic relations. PO3 over PO2 is equal to TO3S over TO2, the whole thing gamma over gamma minus 1. And from that, again, I could get my stagnation pressure at 3. And based on those two, I could get P stagnation 3 also based on compression ratio P2. So depending on the situation that I'm in. that, I could also get TO3. So knowing this, I can deduce the work that is actually being applied on my compressor. So I can say work compressor in is equal to CP, if I'm going to take the kinetic energy into consideration, TO3 minus TO3 minus TO2. That's the work that's being generated across my compressor. Combustor. That one we've done quite a bit, and you're actually working on it for 6. What we have to do for the combustor, it's really the fuel air. So I will say I have fuel air for the burner. I'm going to name it as test. I'm just writing the outline of the equations of how you solve it, and we'll do a quick example problem. But it's exactly the same. Based on FE test, which is the same equation that we written for fuel air ratios, it's TO4 max over TO3 minus 1 over the efficiency of my burner times the heat of combustion, CP TO3 minus TO4 max divided by TO3. So that's my test fuel air ratio. Now, once I get that value, and if I know that value, then I could say if FB test is greater than F stoic, then FB is equal to F stoic. Compute T, the new T4 max, or T4 max. So based on this, I will say TO4 is equal to 1 over 1 plus FB. I'm just rearranging my equation so you have it here. Multiplied by the efficiency of the burner, heat of combustion, divided by CP plus TO3. Just rearranging the terms there. If FB test is less than or equal to F stoic, then FB is equal to FB test. And obviously TO4 is equal to TO4 max. And you can get your pressure ratio from PO4 is equal to R across the burner, whatever losses you have across the burner, PO3. So most likely you're going to be given, if you're working with a real engine in general, that efficiency of the burner is actually provided to you by some previous investigations. Actually, where is, oh, Jason. So Jason is actually working on a journal paper characterizing this efficiency for a ramjet engine. So this is what you're generating. It's through research you get this value. So once you know this value and the heat of combustion of the fuel that you're using and whatever the max temperature material for your combustor, you can figure out, well, my fuel to air ratio that I could run through my combustor, and based on that, my Tmax, which is your adiabatic flame temperature as well. But this efficiency, so unlike when we went here and did a efficiency characterization, this is very heavy experimental research to get. So,
Yeah.
and you might be able to pick it up from journals depending on the situations that you're working on. So turbine. Turbine is the opposite of the compressor. I do have an efficiency through my turbine, which you read before. Where's my curve? What is my efficiency there? T